Hi all, my name is Mads Barnkop from Kaiser Power Electronics. Today it is the circuit analysis of the power amplifier boards and all the system boards for this Nokia Siemens FXEA base station amplifier. So let's have some fun. Let us start out with the pretty peculiar power supply setup. There was this input board which has a lot of noise cancellation handling and the fuses and a large DC bus before going into the three identical power supplies distributing the 48 volt DC out to the base station amplifiers itself. So let's try to zoom in on this and let's just get a good view of it from the start here. As we can see, we have the input plug here to the left. From here on, it goes through these 5 times 10 amp fuses which sits in parallel. Nice gold plated small ceramic fuses. Has a normal common and mode noise choke here along with ceramic capacitors. Passes through two 0.19 microfarad chokes before going into these two Fairchild FDS 3632 100 volt MOSFETs. Now we can see these are sitting between the negative rail and the ground, and it is capacitively coupled to the 40 volt DC. So this could be some kind of earth fault protection. Put the whole circuit ground to normal center ground or to chassis in order to mitigate from some fault conditions. Now, as we move on here, we can see we have a huge bank of electrolytic capacitors. There is a total of 12 220 microfarads capacitors, which then leads to the output to the power amplifiers. As I have seen in many other amplifiers, we have 3 identical power supplies with a single central controller. In this case, it is a LM505035, which is a PWM controller, and it has built-in 105 volt / 2 amp half-bridge gate drivers. Out to the left over here, we have the input plug from the power supply board that we saw before. So over here we have the input sitting on the other side of the board. We can follow the plus 40 volt DC marking here from the choke, and from here on it moves up onto this, another bank of electrolytic capacitors which sit up here near the driver IC in the middle. And here we can see we have the central driver chip, and from here on it distributes out the clock and the driving signal to the 3 power supplies going out to the individual power amplifiers. So let's take a look at those. Okay, so suddenly there is a lot more going on when looking down into the specific amplifier as power supply. So if we take a peek at the analog devices 256 step digital potentiometer here in the middle, we have the separate ground, and then we have the 48 volt DC ground and the 48 volt DC input, which are these 2 plugs. These go directly down to the power amplifier board. The potentiometer here controls the gate driver ICs here, which then through the GTTs drives the MOSFETs, which drives the transformer. And we have a output Schottky diode and choke before we have a conditioned 48 volt DC floating supply out to the power amplifier boards. The power amplifiers, I simply love these circuits, the sheer amount of gold and just the heavy base plate it sits on. It's just a joy looking at this kind of engineering. So let's just jump right into it and zoom in and get all the nice little details. Starting down here in the left corner we have the input plug, and we can see that it immediately goes over a small bridge, which I have not seen before. I labeled this the bridge over troubled water. We can see we actually have 3 PCB tracks running underneath it. Then it goes through another piece here which seems to be white, that there is actually no additional layers between this track and underneath, whereas we can see on some of the other parts that there could be a ground plane or perhaps some other signals going underneath. But it seems here that a lot of effort was done to keep the signals as protected as possible before going into the pre-amplifier chip here, which is a Freescale MW7IC 2040N. Now this is a regular 1800 megahertz with a normal span amplifier, can output a 4-watt signal at 28 volt DC. So this probably only runs on half the power rail. From here on, the output signal, we can follow the output coming out here, goes up through here through this 1P503S hybrid coupler, and we will just get a datasheet up on that. So depending on the configuration on how you input or output of these couplers, you have a certain either phase shift or a blocking of this. And here we can see we have a termination resistor sitting here, but then we have a output that says 90 degrees out of phase going into these other couplers up here, and again it crosses over to the input to the main power amplifier chips here. We also have another termination resistor there, here, crosses over, phase shifted. So once we move up here to the nice big Amplion 250 watt LD mass output transistors, I mean look at those, with double tapped gold plated 2 amplifiers in one package, such a beauty. So from here on we have the signal going up, passing through these chips, and here it is really worth noting the power supply design that sits around these. That has been done a lot of effort to keep the power supply rails at a quarter wavelength out from this to not have it resonate at the same frequency. And up here from the output of these amplifiers, we can see that it is once again combined out here. And just the difference in length of the 2 outputs here suggests that this is a Dorothy amplifier, which is a very clever way of achieving very high efficiency on a small amount of hardware and not investing hugely in something, and you can actually drive this down to very low output levels and also keep a low power usage. I made a separate video on Dorothy amplifiers, so you should really check that out. Now from here on, the signals are both combined through another Anarin Singer 2 3 dB hybrid coupler. So let's just have a data sheet up on that as well. And as we can see, we have the same setup with a termination resistor. It is again combined here, but this time it is combined so both of these goes to the amplifier output, and you have a direct coupler sitting up here. It is the small fingers you can see here. It has a termination resistor at the end. Here we have the output to the output circulator. The output circulator protects the amplifier from reflected energy in the antenna, but you still want to measure how much reflected energy you have if your antenna is badly tuned, and that goes backwards following along this track, going all the way out here in the edge, and we end up down here, goes all the way around the board, and here we have a output plug for the reflected output to be measured. This is the controller board that controls the whole tuning and measurement of how the amplifier is performing. So down here at the bottom you have the 3 white jacks, which goes out to the small motors which control the tuning of the output diplexer, and also for the transmit and receive cavities to tune those to the antenna. And so all the large small signal parts you have sitting up here at the top, which we have here, this is all to measure the reflected energy and transmitting power and all kinds of that stuff. So let's first take a look at how this is controlled and what ICs we have down here. We have a Lattice FPGA, which is the LCMX 0640. It's a 640 LOT, 6.1 kilobit RAM, and has 159 IOs. Now this little controller here controls all these motor drivers sitting down here at the bottom. Each white plug is for each their motor, which we will see from the lid of the transmit and receive diplexer. So let's move up a bit here. Here we have the 2 CPUs which control all of these measurements. It is a Marvel 800E 3018 10 to 100 Ethernet interface we have up at the top here. Underneath we have 16 megabytes of flash memory, and the CPU itself is this Coldfire RISC CPU from Freescale. It comes with a built-in 2-bank DDR RAM, 16-channel DMA controller, and has a fast Ethernet 100 megabit interface as well. So it is a highly integrated circuit in order to have a small package to control some of all these measurements, which will we take a closer look at. It is not easy to track back a signal through a board full of so many surface mount components which you cannot identify. But what goes on here is a lot of hybrid couplers, a lot of switches, and some variable gain amplifiers. So here we have, out on the right bottom side underneath my head, we have the input from the Diplexer, and it is then signal conditioned and amplified throughout this board from right to left. So let's just zoom in and see what we can find out. So starting just over my head, we can see we have the connector here from the Diplexer, and the signal goes up through this NRN Singer 2 XT900 1900E hybrid coupler. Now we also saw this on the power amplifier board, so we now know that this will cross over and is terminated to ground, and we have two signal output lines which goes out here. And it goes into this small hybrid coupler here, but there is also another signal path that we have over here. So we have the signal actually going up above the large coupler here. So what controls the signal flow here and when it goes where? I'm a bit unsure where this is switched around, but it would probably have to do with the different technologies or protocols being used in the receiving part, what kind of signal it is receiving and has to interpret. So from here on we go through another coupler, and we see here the first variable gain amplifiers. And as you can see, all this is really ground stitched to a maximum. There is no room for error here. So these two small amplifiers again output into a coupler, again switched over. Let's see, we will have some outputs probably stitched underneath here to these two switches, which again has some hybrid couplers, and again hybrid couplers, and again hybrid couplers, before ending out in the last hybrid coupler here, again going out in two tracks, moving around the last screw hole here, and we have another variable gain amplifier outputting to a hybrid coupler, and the output from this goes into the last pre-amplified chip before exiting out the plug here. On this board we have all the controls for the transmit and receiving signals. So down here in the left corner we have the three optical inputs, which each go to their FPGA and to the third one over here. The other small chip we saw at the bottom, which was this black one, a Freescale MPC 8377E, which is a 800 MHz PowerQuick 2 CPU. Now this is just a regular small computer which controls the whole interfacing of this board with the system boards. So here we can see it has its main CPU sitting here. It has its Marvel DDR2 RAM, and for the input and output it has these Texas Instruments ACH 973 interfaces along with all its terminating resistors, and the Xilinx Spartan XC3 S200A FPGA sitting over here with 200,000 system gates and 4032 logic cells with 248 user IOs takes care of all these measurements. It also has a small 64 megabyte flash RAM sitting next to it. But here we can see we have a Texas Instruments TLK3131, which is a one-channel 600 megabits per second to 3.75 gigabits per second transceiver, which supports 1 gigabit fiber. And we have, of course, one of these sitting for each Altera hard copy 5 FPGA. So let's move on to the side here. We can see this Altera hard copy 4, which is the HC4 custom ASIC. has a 640-bit MLABs, 9 kilobits of M9 blocks, and 144 kilobits of M144K blocks. So a very high capacity FPGA chip, or ASIC, which controls all the logic that we see up here. This is all the analog to digital conversion and digital to analog conversions, which we'll take a closer look at now. All this talking really makes me thirsty, so before jumping into this whole DAC ADC board, let me just get a nice can of soda. It's a little too early on the day for a beer. It's after all, it's a little over 12 at noon, so yeah, still. Cheers. Now, there is so much going on this board that there is really a certain clear way to follow all the signals. Some of it just goes underneath and pops up here and there. So I will do my best to start out with the ADC part, so we see the receiving part from the Diplexer and how that is turned into the telecom protocol again, and then afterwards follow the DAC, where we have the input coming from the fiber optics and going out to the power amplifier. So let's first dive into the ADC part. So let's first just jump right into the middle of the board here, where we have the transmit receive input and we have the receive input. Now this is these two contact points here, where we have the connections up to the Diplexer. Now from here on we have some ceramic resonator filter modules, which I made another video on detailing on those, so check out that in the description as well. From here on we can see the two signals going up through some additional filters. We have some digital attenuators where you can adjust the signal strength. So here from here on we go up to the analog devices AD5356, which is a 1200 to 2500 MHz dual intermediate frequency amplifier, and in this application it is used as a down conversion mixer, and it is a dual line input and it is also a dual line output. Now depending on which technology you have on the receiving part, there is two analog to digital converters sitting after this. One of these is this analog devices AD9255, which is a 14-bit 125 megasamples per second ADC. The other one sitting at the left side of this, it first goes through a analog devices plus 20 dP dual IF variable gain amplifier sitting here. And from here on it goes down here, the two line outputs of it. And it is a bit hard to follow, but I think we can safely say it's something along these lines through all this filtering. And down here we have a Texas Instrument ADC 16DV160, which is a dual analog to digital conversion, 16-bit at 160 megasamples per second. So judging just from the megasamples per second, I would say that this is the 4G ADC, and over here we had the 3G ADC, and perhaps also used for GSM and other lower tier technologies. So looking at after this down conversion mixer, and we would like to look at the transmit channel, then we have two DACs sitting in this board here. First we have down here for itself a analog devices AD9122, which is a dual 16-bit 1200 megasamples per second digital to analog conversion chip. So this receives a single bit stream from the FPGAs we saw, and it delivers out a analog signal from that single bit stream. Now the output to the power amplifier itself is first found up here. So if we just quickly track that back, we would just take this backwards. We have the output to the power amplifier. Goes through some signal conditioning here, moves up a lot of different switches and measurement points, goes all around here, and it goes through a 8-pole ceramic coaxial resonator block. This is what I mentioned earlier that I made a separate video on explaining how this works. From here on, it comes from this analog devices ADL 5375, which is a 0.4 to 6 GHz quadrature intermediate frequency modulator. And here we have the up conversion. I made a separate video as well on down and up conversion mixers, so you should really check that out if you like to see the technology behind receiving this 1.8 gigahertz signal that you are transmitting on, but when you do the whole data signal conditioning, you are doing this at a much lower frequency. So to support some of all these nice ICs, we have here on the side a Analog Devices ADM 660, which is a CMOS switched capacitor voltage converter, and that sits along with a Analog Devices ADF 4160 6 GHz PLL frequency synthesizer. So this is the clock generating chip that delivers the signal for the up and down conversion mixers. Now all this also needs some ultra fast and stiff power supply regulation. So down here we have a Texas Instruments PT 77701, which is a 1.8 ultra fast regulator. So we also did mention that there was this reflection measurement. So up here we have the input from the reflection from the PA, goes through some filtering, signal conditioning, and ends up in a small variable gain amplifier that did not have any locatable data sheet. And finally, we are at the black magic of radio frequency design, the Diplexer or the Duplexer, depending on what you like to call it. Here we have 3 identical setups, so I have only marked up the one in the middle, and we will take a closer look on how to identify a receive channel and a transmit channel. And I go into much more detail about these Diplexer filter designs in another video, so check out that description, the link in the description as well. So let's check out what goes on down here at the input. Now, it starts out with these 2 wires here, which is the reflection and measurement wires going back into the parts of the system boards where we saw we had connections to measure the reflected energy and also the output power and control of the antenna tuning and cavity tuning and such. Now, as we move up, it is actually easiest to identify the transmit and receive channel from looking at how many couplings you have between the resonating chambers. Now, looking at a chamber like this, that this is a resonating cavity, and once you have these ports between them, that is a coupling, but you can also have these bridges of copper going between them, and that is a more direct coupling where you couple energy past a chamber, or you can actually just couple even more between 2 chambers than just the port here. Then you can see up here that you have all kinds of different couplings, and the more couplings you have, the sharper the edges of your bandpass filter is. So that is what I explain in the other video about diplexers in detail. So if we follow the poles going up here, that for each of these circles we have that I have marked R1, R1 or T6 to 5 as the transmit and receive signals goes in each their direction. That is 1 pole in the filter. So we can see that as we move up here that we have 6 poles in the transmitting filter and we have 5 in each of the receive filters. And that is because it is more important to keep a very narrow band on your transmitted signal than on your received signal, as you have a lot more control over the filtering of the received signal than you have on your transmitted signal. You really need to be that as clean as possible. And up here we have the broken off connectors as the receive transmit part here, and the receiving parts actually just go through these 2 screws here and connect it to the boards. I hope you enjoyed this circuit analysis video of this Nokia Siemens Flexi BTS FXEA amplifier base station system. And I really hope you would like to support my channel by joining it up with a membership or checking out some of my merchandise, which primarily consists of mugs, t-shirts and stickers. So check them out please. And until next time, see ya.